Hey, good morning, good afternoon, good night to everybody. Today we'll discuss about the sound waves, and this is the lecture number 8. We'll cover the following topics: audible, ultrasonic, and infrasonic waves, propagation and speed of longitudinal waves, vibrating systems, and source of sound, beats, and properties of beats, Doppler effect, and some real life examples. Now, so actually we'll discuss about the science of sound, and we'll take 5 minutes from that. Sit and review notes for 5 minutes. The test will begin shortly, and there will be two short answer questions to add your paper. Now, let's set go. In movies and TV, we'll sometimes see and hear things exploring in outer space, alien, spacecraft, and things like that. Okay, is that really possible to hear sound in space? Why or why not? Explain your answer and using what we know about sound. Actually, this is a great question for you and everybody's question. What do you hear actually from this movie or drama? Actually, we did you hear something? Maybe the sound you hear was quite as your cat licking her paw, or maybe it was loud like a siren going by you. Is it possible to you? Sounds are everywhere, and you have two pole parts on your body that let you hear them all your ears. No matter where we go, sound waves are all around us. So sound, close your eyes and listen to the sound. Actually, if you click this, you will hear the 6 types of sound. Actually, you can hear from internet actually. So we'll hear 6 types of sound there. So what is sound? This is our main question. And sound is a form of energy that can be heard and travels in waves. So when matter vibrates or moves back and forth very quickly, a sound is made. That means a sound wave is made. So sound waves can travel through solids, liquids, or gases. That means sound waves must need a medium. That's maybe solids, liquids, or any type of gases. For example, when a school bell rings, parts of the bell will vibrate, creating sound. So how does the ear work? Sound waves are sent. The outer ear catches the sound waves. The middle ear takes the sound waves and vibrates the eardrum. The inner ear sends the message to the brain. That means our brain is actually totally a machine, a complex machine, and sound waves is creating from the source and outer ear hearing and entering as a wave, the sound waves. And after middle ear, there is a inner ear. So, and we'll get the sound. So the brain puts it together and hooray, you hear your favorite song on the radio. In this way, we hear songs or we hear the sound of movies, etc. Now sound travels in waves, and sound must travel through a matter to be heard. And remember that matter can be a solid, a liquid, or gas. That means medium will be must present. A sound is made when things vibrate. Sound travels by sending vibrations through matter. We hear our telephone or mobile phone with the discussion of our neighbors or relatives who is staying in USA or in Europe, etc. countries, and we hear their sounds or speech easily in this way. That means sound travels by sending vibrations through matter. Now sound travels through matter, you must know, gases. And most of the sounds here travel through gases such as air. Sound waves travel slowly through air. You must know this. For example, sound formed from a bell, a horn, or an alarm clock travels through the air. From the liquids, some sounds that we hear travels through water. Sound waves travel faster through water than through the air. Remember, this is a great point for us. Sound waves travel faster through water than through the air. So sonar is the way to use sounds to locate objects underwater. When a ship travels from on the sea and we hear the location of another ship or another bodies with the help of sonar. And sonar is the way to use sounds to locate objects underwater. So what animals use sonar? This is a great question for us. Another one, solids. Some sounds that we hear travels through solids. Sound waves travel very fast through solids. For example, when you heat a drum, it vibrates, then the sound travels through the air to hear your ear. Sound makes the air vibrate. You must know in an aircraft, when a man travel moon or any other planet. So for sound to be heard, sound vibrations must have air or some other kind of matter to travel through it. And you cannot hear sound in outer space because there is no air or other matter to carry sound vibrations. So how do you think astronauts are able to talk each other in outer space? This is a great question for you. How to talk the astronauts to each other, actually with the help. Now think, sound can also be blocked. Think, why do some people wear ear covering? Cover your ears. Some people who work near loud machines wear ear coverings. That means more sounds can hamper our brain and our memo and our can heat our air directly. This is why more sounds have great impact on our body and our health. So the covering blocks some of the sound vibrations from reaching the ears. The ear or covering protect your ears from the noise. Have you ever covered your ears? Why? Actually, audiologist. That means who is the specialist on sound. So an audiologist is a person who tests people's hearing. They use special machines that make sounds. They also help people who do not hear well, dumb. Have you had your hearing tested? Actually not. So how you make sounds? We use our vocal cords to make sounds in our throat. So you must know about the vocal cord, which is very important for making sound in our throat. Another one, when we speak, our vocal cords vibrate. And place your hand on your throat. When you talk, and you can feel the vocal cords vibration. So loudness or volume means what? Volume is the loudness or the softness of a sound. Okay, volume is the loudness or softness of the sound. Loud sounds use a lot of energy and soft sounds use a little energy. So for example, the harder a drum is hit, the more the drum will vibrate. The more an object vibrates, the louder sound it makes. So what is pitch? You must know about the pitch. Pitch is the highest or lowest sound an object makes. So what is pitch? Pitch is the highest or lowest sound an object makes. The object that vibrates slowly make a low pitch. For example, of low pitch will be drum. Object that can vibrate quickly make a higher pitch. For example, a recorder. Now, you must know about music. Music is a combination or sequences of sounds that people enjoy listen to. Musical instruments make different sounds by plucking the strings. The shorter the string, the quicker it vibrates, producing a high sound. The longer the string, the slower it vibrates, producing a slow sound. So let's review. Sound is a kind of energy that can be heard. We have to remember that what is sound. So we can say sound is actually energy. A sound is made when things vibrate. The vibrating objects makes the air around it vibrates. So sound vibrations move through the air into your ears and make the eardrums vibrate. So volume is what? What is volume or loudness? Volume is how loud or soft the sound is. And pitch is what? Pitch is how high or low a sound is. Okay. So sound energy, actually sound travels on a longitudinal wave. We must know about the types of waves in our previous lecture. There are two types of waves. One is transverse waves, another is longitudinal wave. So we have to remember that sound travels on a longitudinal wave. That means there is an intensity and frequency. And so notice that the sound travels in a spiral form like a spongy, like that. So imagine that what happens when you drop a stone into a pool of water. Actually, waves ripple out from the spot where the stone entered the water. The way waves move across the water is similar to how sound waves travel through the air. Actually, look like that. So when you speak or shout, your vocal cords vibrate. These vibrations travel in all directions through the air as waves. When the waves reach our ears, they make our eardrums vibrate too, so we can hear the words in this way. This is actually how we can hear a sound wave. So sound waves travel on a medium, must be solid, liquid, or gases. Sound travels by pushing the particles of a substance. The particles push into the particles next to them and then return to their original position, and the sound continues to travel in this form until it reaches your ear in this way. So you must know from our previous lecture, longitudinal wave creates actually two parts. One is compression, another is rarefaction. So by making compression and rarefaction, in this way, longitudinal wave travels and we hear the sound. Okay. So which state of substance would sound travels through the faster? Actually, this is a question: solid, liquid, or gas. You must know. It's time to let your partner hear. Plus domino effect. Okay, compression and refractions. So compressions, area of sound waves where molecules are closer together, and rarefaction means what? Area of sound where molecules are farther apart. In this way, making sound wave travels through any medium by using compressions and rarefactions. Okay. So what is wavelength? You must know. Wavelength distance from end of compression to the end of the next compression. So this is the air molecules, and this is the compression, and this is another compression. This is compression. This is the last compression. So stereo speaker, this is a speaker which is producing sound wave, and this is the wavelength. Now, compression increased air density. Okay, rarefaction, rarefaction. So rarefaction means decreased air density. Now what is frequency? Frequency is the number of waves produced per second. So frequency means you must know the number of waves produced per second. Its unit is hertz. So two other properties that affect sound energy, pitch and intensity. So what is pitch actually? Pitch is the rate at which the vibrations are produced. The higher the frequency, the higher the pitch. You must remember this. Which pictures more above would have the lowest pitch, highest pitch? You must know the higher frequency, the higher pitch. So the third one is the actually higher pitch. And the first one is the what? Lower. Now, the more waves per second or the higher the frequency, the high. So lower pitch and higher pitch is this is the example for that. Now what is intensity of a sound wave? The intensity depends on the strength or amplitudes of the vibrations producing the sound. If a piano string is struck forcefully, the string swings back and forth in a wider arc. The stronger vibrations then produces a louder tone. Since the stronger vibrations compresses the molecules of the air more forcefully and gives them greater energy, which is interpreted by your ears as a louder sound. So you must know from this example about the intensity of a sound wave. So conclusions actually we have discussed here. So this is the sound wave. They reach the wall at the same time, these two waves. Okay, this is the sound. They reach the wall at the same time. Doubling the frequency of a wave source doubles the speed of the waves. The speed of a wave is unaffected by changes in the frequency. It is affected by the actually medium. So you must know about this answer. Now another two waves are traveling through the same container of nitrogen gas. Wave A has a wavelength this and B has the wavelength. The speed of B must have 1/9 or 1/3 or the same as what will be the answer is actually the same. Why do we hear this when a jet flies past us? The closer the jet is to our ears, the closer the wavelengths. Therefore, we hear a higher pitch when the jet is closer. Jet means actually this may be rocket or any airplane or any plane above under the sky, and lower pitch as it moves farther away. We hear big sound from the airplane when it's very near to our ear. So the closer the jet is, more intensity, and therefore it seems louder to us. So label the three pictures below the following: higher pitch, middle pitch, lower pitch. This is the pitch. So you have learned how sound travels. 3 cheers for the ears. Okay. Now, so from this we can tell that what is sound. Sound is a kind of energy. Sound is made when objects vibrate or move back and forth quickly. So sound waves is a form of energy that travels as wave through a matter, and a wave is a change that carries energy from one place to another. Parts of a sound wave. A sound wave goes up and down. It has high points and low points, and high points is called crest and low points is called trough. So frequency, what? Frequency is the actually number of crest or troughs that passes by over certain amount of a time. This is the frequency. And sound wave, this is the example of sound wave. This is the crest, and this is the trough. Between two crests, it is called wavelength. How sounds are made? Is made when something vibrates. For example, when you play a guitar, the sounds come from the strings, etc. So how we hear sound? You hear sound with your ear, outer ear, and eardrum, and when sound waves hit the eardrum, it vibrates. So how do we hear sound? Actually, in this way: middle ear, inner ear. Now, properties of sound. Sounds can only travel through the matter. That matter is called a medium of the sound, and the medium can be solid, gas, etc. So temperature also affects how fast sound moves, waves moves, and sound waves move faster when the medium is warm. They move slower when the medium is cold. Now, what is pitch? The pitch of a sound is how high or low the sound is. Pitch is the caused by the frequency of the sound, and high frequency waves makes the high pitch, and low frequency waves the low pitch. The volume or loudness. Volume is the how loud or soft the sound. The volume depends on how much energy sound wave lasts. So if the amplitude is large, the volume will be loud, and the amplitude is small, the volume will be soft. This is the actual example for. Now controlling sounds. A sound volume is measured by decibels. An amplifier is a tool that makes sound louder. Materials like soft cloth, foam, rubber, plastic make sound softer. Now acoustic or echoes, what? Acoustic is the study of how sounds travel and can be controlled. When a sound wave hits something that is heard, like a wall, most of the waves bounce off the wall. This causes an echo. Some of the wave echoes through the wall. A sound wave may hit something that is soft like cloth. Then most of the wave will be absorbed or taken in by the cloth. So this is actually we have discussed in our this slide. So we must know what is the echo. It is heard by reflection of sound wave from the extended reflector, like a big wall or cliff of a high mountain or a hill, and is distinguished from the original. So the human ear unable to distinguish two sounds unless the time interval between them is 0.1 second. So when a sound produces echo, the time interval between the echo and the original sound must be at least 0.1 second. The original sound must go to the reflector and come back. If the distance of the reflector be as meter, and it will travel a distance twice as meter. So sound travels 332 meters per second. So S equals to what will be 332 multiplies 0.1 divided by 2 meters. That means 16.6 meters should be the minimum distance of the reflector. Again, a man ordinarily requires 1/5 second to utter monosyllabic word. So there must be at least 1/5 second interval between the utterance and the monosyllabic and reception of sound. So accordingly, the distance of the reflector should be at least 1/5, 1/2 into 332 multiply 1/5 meters. That means 33.2 meters from the source. So we have to remember about these two properties of echo. Now, technical application of sound wave reflection. Actually, the depth of a sea from the moving ship by the help of echoes have a large importance. There are many ways of finding the depth of a sea level or any way, any well. They are divided into two groups: one low frequency sonic system and high frequency supersonic system. So now what will be the reflection of sound wave? uh, we know about this. Is the look like a reflection of light. Now what will be the interference of sounds? Interference is the inherent properties of the wave motion. This is due to superposition of the wave of the same period meeting at points in a medium. So let's two waves traveling along the same directions be represented by y1 equals to a sine twice pi by lambda ct minus x, and another is b sine twice pi by lambda ct minus x plus alpha. This is the another phase in equation 2. So alpha is the actual difference phase, and A and B are the amplitudes. Lambda is the wavelength, and C is the velocity of wave propagation. So by the principle of superposition, we get y equals to y1 plus y2 as sine twice pi by lambda ct minus x plus b sine twice pi by lambda ct minus x plus alpha. So this is actually a sine theta plus b sine theta plus alpha. Now here theta equals to twice pi by lambda ct minus x. Now we can find y equals to a plus b cos alpha sin theta plus b sin alpha cos theta. That means a equals to a sin theta plus epsilon. So here a plus b cos alpha equals to a cos epsilon and b sin alpha equals to a sin epsilon. So in this way, alpha equals to 0, twice pi, etc. Where a is not equal to b, that means though two amplitudes are not equal, and if the amplitudes are equal, we get this figure. And if the amplitudes is not equal, but phase difference is pi, thrice pi, etc., that means odd, right? Odd with pi. Another one is equal, equals to pi. So squaring and adding, we get capital I equals to root over a square plus b square plus twice ab cos alpha, and epsilon equals to this. Now y equals to a sine twice pi by ct minus x plus epsilon equals to what will be when alpha equals to 0, twice pi, 4 pi, etc. even multiple of pi, and capital A, that means the amplitudes of supersonic wave, super composition wave a plus b equals, if a equals to b, and amplitudes, higher amplitudes will be twice a, and alpha equals to odd multiple of pi, then amplitudes equals to a minus b if a equals to b and a equals to 0. So actually that's when the phase difference is multiple of twice pi, that path difference is the actually multiple of lambda. So two waves will reinforce each other and intense sound is here. When the phase difference is odd multiple of pi, that is path difference is lambda by 2 or its odd multiple, two waves will destroy each other. So when amplitudes are different, very feeble sound will be heard. So no sound will be heard when the amplitudes are the same. They are represented graphically in figure. So interference of sound wave can be directly demonstrated by the actually this. So in this way, there are four figure. Okay, this is for odd multiple of pi, and this is for even multiple of pi, and this is the destruction. We cannot hear the sound here. Okay. Now, very important parts, beats. What will be the beats? Composition of two waves, slightly different frequencies, velocity of propagation being same. If two components of wave that travel along the same direction are not very shortly, but very nearly of equal wavelength, the resulting wave motion represents peculiarities. So it is not harmonic. The resultant amplitude is greater in some places than in other, so that the actual waves consist of condensation and rarefaction. So let the phenomenon of destruction and reinforcement of two sounds together is called beat. So this is the definition of beat. Let the displacements y1 and y2 at a place due to wave having same amplitudes are given by y1 equals to s sine twice by lambda 1 ct minus x, and another one is y2 equals to s sine twice by n1 t s by lambda 1. This is actually converting the components as c divided by lambda 1 equals to n1, considering. And another wave equation y2 equals to s sine twice by lambda 2 ct minus x, and this can be converted to s sine twice by n2t divided minus x by lambda 2. This is equation number 6. And here n2 equals to c by lambda 2, where n1 is the frequency of first one and n1 equals to n1 plus b of the other. The difference in frequencies is b of two waves, which produces the difference in wavelength. The resultant will be what? Y equals to y1 plus y2. That means s sine twice pi by lambda 1 ct minus x plus s sine twice pi by lambda 2 ct minus x. Actually, this is the equation of sin c plus sin d. Sin c plus sin d, you must know about 2 sin c plus d by 2 and cos c minus d by 2. Okay, you must know about the formula or identity of trigonometry. Sin c plus sin d identity. So twice a sine this plus this divided by 2 will be twice pi by 2, 1 by lambda 2 plus 1 by lambda 1, and this one. But 1 by lambda 1 minus 1 by lambda 2 equals to what? 1 by lambda minus 1 by lambda plus d lambda. So this equals to d lambda by lambda square, and 1 by lambda 1 plus 1 by lambda 2 equals to 1 by lambda plus 1 by lambda d lambda. This equals to 2 by lambda. Or we can write y equals to twice a cos twice pi by lambda dash ct minus x sine twice pi by lambda ct minus x. This is another equation. And lambda dash equals to what will be here? Twice lambda square divided by d lambda. The wavelength, the wave of wavelength lambda advances with periodic vibrations of amplitudes, which has a wave character of wavelength lambda dash. This lambda dash equals to this one, twice lambda square divided by d lambda, advances with the same velocity c as the original wave. The resultant displacement is given in the following figure. So the distance between two consecutive maxima or minima is lambda dash by 2 equals to lambda square by d lambda. This equals to lambda 1 lambda 2 divided by lambda 2 minus lambda 1. The time interval between two maxima or minima is given by distance by time equals to what? This one. Distance by velocity. This is the distance. This divided by c. This whole distance divided by c equals to this. Hence the frequency of the occurrence of beats will be what? This distance by velocity by distance, the frequency. Okay, f equal to b lambda, b equal to f lambda. So f equals to b by lambda. So c lambda 1 by lambda 1 minus 1 by lambda 2. This equals to actually 1 minus n2. Thus, beats produces the periodic fluctuation of the loudness of sound. So phase velocity and group velocity, what will be? The composition of a train of wave differing slightly in frequency, in wavelength, and traveling with different velocities. So in this way, the equation of a plane progressive wave is this. And we can write s sine omega t minus kx, where omega equals to twice pi by lambda c and twice n pi. C equals to n lambda. N is the frequency, lambda is the wavelength, and c is the velocity. B equals to f lambda, like this. So k equals to twice pi by lambda. In this way, we can write this. So in this way, that we get an equation which is a differential equation for that. Now the displacement due to two waves of equal amplitudes will be y1 equals to this and y2 equals to this. Now the resultant will be sin c plus sin d. We get the same procedure. So in this way, 1 by lambda 1 minus 1 by lambda 2 equals to 1 by lambda square by d lambda. And c1 by lambda 1 minus c2 by lambda 2 equals to this. So the equation 15 becomes, okay. The above equations represent the periodic vibrations of amplitudes of the original wave as a resultant of superpositions. These periodic vibrations possesses wave character of wavelength 2 lambda square by d lambda, advancing with a velocity given by c is equals to this, where cz is called the group velocity of the wave. If the dc by d lambda equals to 0, then the group velocity will be the equal to the velocity of the phase velocity are equal. So as found in the previous case. Now what is stationary and standing wave? This is the actually resultant and different phase, and this is the components. The figure 2 represents two similar train of waves moving the opposite direction through the same medium and the resultant. So 5 different instants, 0, t by 4, t by 2, 3, t by 4, and t, where the t represents the time period of the vibrations of the particle. Let two waves of the represented by y1 equals to this and y2 equals to this is the forwarding and this is the backwarding. Okay, then the resultant will be what? Y equals to y1 plus y2. This forwarding, this is y minus, and this is the backwarding, this is y opposite plus. Now resultant will be this. The slope of the train or strain or curve dy by dx equals to this, and the velocity of the vibrating particle dy by dt equals to this one. So acceleration will be this double differentiation with respect to time, and again d square y by dt square will be this. Similarly, c square d square y by dx square will be this. From these two equations we get, this is the characteristic equation of a stationary wave. When cos twice pi by lambda x equals to 0, then y equals to 0 and dy by dt equals to 0. So dy by dx is maximum at a place given by this. This means odd, twice m plus 1 by 5, odd right angle, where m is an integer, or x can be written as like this. Thus there are points at regular interval which are never displaced. These are called nodes. The distance between two consecutive nodes is lambda by 2. The displacement will be maximum or minimum at place given by cos twice pi by lambda x equals to plus minus 1, or twice pi by lambda x equals to m pi. M is integer or 0, so x equals to m lambda by 2, and pi is cancelled from both sides. Or instant given by sine twice pi by lambda c t equals to plus minus 1, or t equals to odd into pi by 4. That means thus there are points at regular intervals where the particles periodically attain their maximum value twice a and minimum value minus twice a, where the strain twice dy dx equals to 0, the velocity is maximum, and these are called antinodes. The distance between two consecutive antinodes is lambda by 2, and between a node and next antinode is lambda by 4. So in a stationary wave, all particles are a state of vibrations except where there are nodes which are at rest. All the particles between two consecutive nodes have the same phase but differ in amplitudes. The particles on the composition side, opposite sides of each node move in opposite direction, hence they are opposite phase. Now this is the distinguish between the progressive and stationary waves. What's the difference between a progressive wave and stationary wave? A progressive wave is a single train of waves which processes along a certain direction in a medium. And on the other hand, stationary wave, it is produced by superposition of two trains of the wave moving on opposite direction. In progressive wave, each particle will execute simple harmonic motion of the same period and amplitudes with different phase depending on the position and of the particle. On the other hand, in a stationary wave, each particle in the medium with certain exception executing simple harmonic motion with same period and phase but with different amplitudes depending on the position of the particle. So there are actually 7 differences between progressive and stationary wave. Now acoustic shade or diffraction of sound. Actually the region behind the obstacle placed before the sound source where the sound is absent is known as acoustic shadow. So properties of sound, actually a sound wave, this is a longitudinal wave, and properties of sound, we have studied this. Sound travels in different mediums with this velocity, and in air, medium, liquid medium, solid medium, the sound speed or sound velocity is this table, and speed of sound different media at 20 degrees centigrade. In water 1482, but in air 343. So loudness is determined by intensity. Loudness depends partly on the energy contained in the sound wave. Intensity describes the rate at which a sound wave transmits energy through a given area of medium. Intensity depends on amplitudes of the sound wave, your distance from the source. The greater of the intensity of sound, the louder will be sound. So this is the common decibel levels. Actually 0 decibel, the softest sounds you can hear, and 20 decibel whispering, and purring cat 25, normal conversation 60 decibel. Okay, so lower, this is the actually range. Pitch is determined by frequency, and pitch, high frequency sound waves high pitch sound, low frequency sound waves low. You can hear sound waves in a limited frequency range, and any sound with a frequency below range of human hearing is known as infrasound. So infrasound means slow vibrations of frequency lower than 20 hertz. Any sound with a frequency above human hearing range is known as ultrasound. So ultrasound means any sound wave with frequencies higher than 20,000 hertz. So this is the example of ultrasonic and infrasonic. The sound of whale is infrasonic, and sound of bat will be. The most instruments produce sound through the vibrations. So this is the actually more usable. Now, what is the resonance? A phenomenon that occurs when two objects naturally vibrates at the same frequency. So natural frequency, and one object can cause another object to vibrate through resonance. When you hear music or a concert, you must hear about the resonance. So the human ear is a sensitive organ that senses vibrations in the air. Vibration pass through the three regions in the air. We must know this. This is the ear. We hear the sound wave. And how are the reflections of the sound waves used? Reflected sound waves are used to determine distance and to create image. Some ultrasound waves are reflected at boundaries. So ultrasound imaging is used in medicine. Ultrasound, so ultrasonography. Okay, ultrasonography is very common test of doctors for anybody's. So ultrasound imaging is used in medicine. The echoes of very high frequency ultrasound waves between 1 million and 15 million hertz are used to produce computerized image used sonogram. Remember, this is the best use of sound in our medical history. So sonogram, ultrasound and sonar. A sonar system determines distance by measuring the time it takes for sound wave to be reflected back from a surface. So ds equals to bt, distance equals to velocity multiplied time. This is the way to determine the distance of any objects under the ocean or a pond or a river by using the properties of sound, that means sonar. So the characteristics of sound, sound can travel through any kind of matter, but not through a vacuum. The speed of sound is different in different materials. In general, it is slowest in gases, faster in liquids, and faster in solids. So the speed depends somewhat on temperature, especially for gases. This is for different speed for different materials. And this is the loudness related to intensity of the sound. Pitch is what actually related to frequency. Audible range will be 20 hertz to 20,000 hertz. Upper limit decreases with age. Ultrasound above 20,000 hertz, and infrasound will be what, below 20 hertz. Now this is the decibels for different source of sound. The intensity of a wave is energy transported per unit time across a unit area. This is the definition of intensity. The human ear can detect sounds with the intensity as low as 10 to the power minus 12 watt per meter square and as high as 1 watt per meter square. So perceived loudness, however, is not proportional to the intensity. Now, the loudness of the sound is much more closely related to the logarithm of the intensity. The sound level is measured in decibel and is defined by beta in decibel equals to 10 log I divided by I naught, where I naught is taken be the threshold of hearing. That means this is the constant I naught equals to 1.0 into 10 to the power minus 12 watt per meter square. For example, the sound intensity on the street at a busy street corner, the sound level is 75 decibel. What is the intensity of sound there? This is the intensity. Now another example for a loudspeaker responses. A high quality loudspeaker is advertised to produce at full volume frequencies from 30 Hz to 80,000 Hz with uniform sound level plus minus 3 decibel. That is, over this, the frequency range, the sound level output does not vary more than 3 decibel for a given input level. By what factor does the intensity change for the maximum change of 3 decibel in the output sound level? We are given the change in intensity beta 2 minus beta 1 equals to 3 decibel. We have to find I2 divided by I1, this ratio. So beta 1 minus beta 2 equals to 10 log I2 divided by I0 minus 10 log I1 divided by I0. So in this way, we can find 2.0. Another example for you, this is left for you. Trumpet players. Another example for you, how to find the sound level at 300 meter. So first of all, the intensity is sound is I1, sound level beta 1, and beta 1 equals to 140 decibel. At 300 meter sound intensity I2, sound level beta 2. But we remember that intensity is proportional to 1 divided by distance whole square. This way we can find 120 decibel. Another, how teeny the displacement is. Calculate the displacement of air molecules for a sound having a frequency of 1000 hertz at the threshold of hearing. You must know I equals to P divided by S, where P is the twice pi square rho S I F square S square by T, twice pi square rho B F square S square. So just using, we get A equals to this one. Now intensity of, we hear the sensitivity varies with the frequency. These curves translate the intensity into sound level for different frequencies. So this one is the actually main chart for this part. This is the general expression of wave equation, and del square y by dt square equals to d square del square y by dx square. For the standing wave, the part of a body oscillation in harmonic motion at the same angular frequency. Suppose the general expression of standing wave, we can write yxt equals to x sine omega t plus phi. Substituting this into the wave equation, we get minus omega square x equals to what will be d square y x by dx square. The general Solution of the equation will be x equals to s sine omega by b, x plus b cos omega by bx. So we can write s sine kx plus b cos kx. So the general solution of the displacement of the standing wave will be this. But the vibration of the string fixed at both ends in the expression by this. This is the example. And y1 is this and y2 will be this. And the equation of the components wave and what is the distance between two consecutive mode of the stationary wave. You must know y1 plus y2 equals to this sin c plus sin d formula 2 sin c plus d by 2 cos c minus d by 2. So comparing with the given wave equation, a equals amplitude c1, lambda equals to 6. So twice pi b by lambda equals to this one. This way we can write the two wave equation y1 equals to and y2 equals to. Distance between two consecutive node is lambda by 2 equals to 3 meter. Now that this is example. A high frequency radio receiver receives simultaneously two signals from a transmitter 400 kilometer away by a path along the surface of the earth and the other by reflection from a portion of the ionospheric layer situated at the height of 200 kilometer. So the distance d, length of the direct path along the earth's surface, and s is the height of the reflecting ionospheric layer. The path difference p between the two routes will be p equals to 2 into s square plus d square by 4 to the power half minus d. Now interference takes the place between the signals arriving at receiver by the two routes. So differentiating with respect to t, we get dp by dt equals to twice s into s square plus d square by 4 to the power minus half dh by t. That means with respect to t. Differentiation with respect to t. But we know frequency equals to f, b equals to f lambda. That means from that relation we can write f equals to b by lambda. So dp by dt, f equals to 1 by lambda, dp by dt, and b by c, dp by dt. Where b is the frequency of the radiation and c is the speed of light. Thus, in this way, we have ds by dt equals to cf 2bs s square plus d square by 4 to the power half. So this is the figure for this to find out the height is, and this is the transmitter and earth surface and receiver, this one. So just putting the values, we get the result. We are given height equals to 200 kilometer and d equals to 400 kilometer. So velocity will be 10 multiplied 10 to the power 6 hertz is given for you. This is another example. This will be for you. To left for you. This is for sound wave. Just summing y1 plus y2, then we get the relation. This is the relation between phase velocity and group velocity. Okay, good morning, good afternoon, and good night to everybody. Today we'll discuss about sound waves and Doppler effect. Actually, this is the last chapter, and we'll focus on actually Doppler effect. First of all, we review the sound waves. First of all, we'll review the sound wave. First of all, what is sound? The nature of sound, ears and speakers. And sound is really tiny fluctuation of air pressure, and units of pressure Newton per meter square or psi, and carried through air at 345 meter per second. That means velocity of sound in air, and 770 mile per hour as compressions and rarefactions in air pressure. This is the actual longitudinal wave and compression, and this is the rarefaction, and this is the compression, and this is the rarefaction. This occurs due to the pressure of compression. So distance between two compression or distance between two rarefaction is called wavelength. This is the compression and this is the rarefaction. That means density big, high density makes compression and low density make rarefaction. What are the properties of sound wave? Actually, we must know wavelength is measured from crest to crest or trough to trough or upwing to upwing, etc. That means this is the wavelength. And to complete making of this wavelength is called time period, capital T. For traveling waves, sound, light or water, there is a speed C. Frequency F refers to how many cycles passes per second, measured in hertz, and T equals to capital T, that means time period equals to 1 by frequency. And these three are closely related. C equals to F lambda or B equals to F lambda in other books. So there are two waves, longitudinal versus transverse. Sound is longitudinal wave, meaning that the main motion of particle is along the direction of propagation. And transverse waves, water waves, light waves have things moving perpendicular to the direction of the propagation, making densely and rare. That means compression and rarefaction moving along the wave. So why sound longitudinal? Actually, this is a great question for us. Waves in air cannot really be transverse because the atoms and molecules are not bound to each other. Can't pull a momentarily neighboring molecule sideways. Only if a rubber band connected the molecules would this work. Fancy way of saying this, gas cannot support shear loads. So air molecules can really only bump into the another. Imagine people in a crowded train station with hands in pockets. So pushing into crowd would send a wave of compression into the crowd in the direction of push, longitudinal, jerking people back and forth sideways over several meters would not propagate into the crowd. But if everyone held hands bonds, this transverse motion would propagate into crowds. This is the real life example to understand why sound is longitudinal. The sound wave interference and beats. When two sound waves are present, the superposition leads to interference. By this we mean that constructive and destructive addition. Two similar frequencies produce beats, spends a little while a phase and a little while out of phase. result is weighting of sound amplitudes. So in phase weight, this is the single A and signal B, and this is the signal A plus B. That means interference occurs, beat, out of phase cancel. Okay. Now speed of sound in air is related to the frantic motions of molecules as they jostle and collide. Since air has a lot of empty space, the communication that a wave is coming through has to be carried by the motion of particles. For air, this motion is about 500 meter per second, but only about 350 meter per second directed in any particular direction. So let's have faster sound speeds because atoms are hooked by the string. That means there is a bond. So don't have to rely on atoms to traverse gap. Spring compression can does travel faster than actual atom motion. So sound, what is sound intensity? Sound requires energy pushing atoms or molecules through a distance and therefore a power. Sound is characterized in decibel according to sound level. And example is this for you. We have discussed in our previous lecture. Sound hitting your eardrum. This is also we have learned in our previous lecture. This is review one. Sensitivity of the human ear. This is the actually range of hearing sound 20 hertz to 20,000. So the impressive range of 3 decades logarithmically about 10 octaves factors of 2 compare these two vision with less than 1 octave. This is the frequency difference between hearing level. Or speaker geometry we are using in our real life. Actually use the to make sound wave. Push me and pull me. Cone movement, push. This is the magnet. When the center of the speaker cone is kicked, the whole cone can't respond instantaneously. The fastest any mechanical signal can travel through a material is at the speed of sound in the material. So in this way, sound wave propagate. The looks of sound waveform, frequency, content, digital sampling, all shapes of waveforms. Different instruments have different waveforms. Glockenspiel, soft piano, loud piano, trumpet. Our ears are sensitive to the detailed shape of waveforms, more waveforms. How does our ear know? Our ear pick out the frequency components of a waveform. A DC constant signal has no wiggles, thus is at 0 frequency. And this is the one. A sinusoidal wave has a signal frequency associated with it. This is the faster wiggles. And the height of the spike indicates how strong amplitudes that frequency component. This is the different phase. Composite waveform. This is the description. This is the time series, Fourier expansion, and power spectrum. This is the decomposition as square wave. We have to use Fourier series to expansion of a square wave. This is the real life application of in engineering. Fourier series for k equals to 1, 5, k equals to 11, k equals to 49. The air assesses frequency content like this by waveform. Now we will discuss about actually what is Doppler effect. What is Doppler effect? We'll discuss now. So if source moves away, light appears redder than it is. If source moves towards us, light appears bluer. So visible light regions of the electromagnetic spectrum, the shift of the light waves is proportional to the relative speed of the source and the observer. This is the main properties of propagating wave. So Doppler shift, what is the Doppler shift? Wavelength is shorter when approaching and stationary wave is in the middle. Wavelength is longer when receding, okay? When approaching and when opposite, wavelength is longer. So in laboratory spectrum, comparison of laboratory of to blue shifted object, reference lines from laboratory source and absorption lines from star. This is the reference lines from laboratory resource, absorption lines from star. Wavelength shift, what will be the wavelength shift? Assume radial speed b of glowing object is small compared to speed of light c, where the velocity is more and more less than the velocity of light, then lambda naught is reference wavelength of medium at rest. In that case, the difference change in wavelength divided by original wavelength equals to lambda minus lambda naught divided by lambda naught equals to minus b by c. So frequency shift will be like this. Change in frequency divided by original frequency equals to f minus f naught divided by f equals to b by c. So example of calculation, the star Vega has a hydrogen line of 656.255 nanometer, which is shifted from the reference value of 656.285 nanometer. Is it moving towards us or away? Calculate its speed. Red shifted to longer wavelength, so moving away. Speed is actually minus 13.7 kilometer per second. Rotation rate from the Doppler shift. This is the slow radiation. This is the fast radiation. Slow radiation because narrow spectrum lines indicates that star A is rotating slowly, and wide spectral lines indicate that star B rotates rapidly. This is the normal curve in statistics. We learn from normal distribution. Discovery of planets around remote stars. Orbits of unseen planet. Rotation of speed galaxy from 21 centimeter spectral line atomic hydrogen. Historically, actually, Doppler shift Edwin Hubble observed that the universe is expanding. Using these properties of Doppler effect, Edwin Hubble observed that the universe is expanding. So what Hubble found, the Hubble constant is not equals to 558 kilometer per second, is the slope of this graph, and comparing this to Mason in 1931. So according to Hubble's law, velocity equals to h naught multiplied d. H naught is called the Hubble constant. It is generally believed to be sound 65 kilometer per second per MPC, plus or minus about 10 kilometer per second MPC. The farther away you are, the faster you are moving. So according to the Hubble. So implications of Hubble's law, distance equals to velocity divided by Hubble constant. So to get a rough idea of how far away a very distant object is from Earth, all we need to know is the object's velocity. The velocity is relatively easy for us to measure using Doppler effect or Doppler shift. Space between the galaxies expands while galaxies stay the same size. Systematic expansion. This means this expanding in a big way form. So now, what is Doppler effect? Actually, as a wave source approaching, an observer encounters waves with a higher frequency. As the wave source moves away, an observer encounters wave with a lower frequency. And the Doppler effect, this apparent change in frequency due to the motion of the source or receiver is called Doppler effect. This is the actual definition of Doppler effect. The greater the speed of the source, the greater will be the Doppler effect. Doppler effect sites we have used here. So imagine a bug jiggling its legs and the bobbing up and down the middle of the quiet pool. The crest of the wave it makes are concentric circles because the wave speed is the same in all directions. If the bug bobs in the water at a constant frequency, the wavelength will be the same for all successive waves. The frequency is the same as the bug bobbing frequency. So Doppler effect, the bug maintains the same bobbing frequency as before. However, an observer at B would encounter a higher frequency if the bug is moving towards the observer. And each wave crest has a shorter distance to travel, so they arrive more frequently. Each crest has to travel further than the one ahead of it due to the bug's motion. So this is the due to Doppler effect. Now, another example of Doppler effect, sound. The Doppler effect causes the change in pitch of a siren. When a fire truck approaches, the pitch sound higher than normal because the sound wave crest arrive more frequently. When the fire truck passes and moves away, you hear a drop in pitch because the wave crest are arriving less frequently. So this is the example. The change in loudness is not the Doppler effect, it is the shift in frequency. Okay, you have to remember this one. The police use the Doppler effect to radar waves to measure the speed of cars on the highway. And radar waves are electromagnetic wave. Police bounce them off moving cars. A computer built into the radar system compares the frequency of the radar with the frequency of the reflected waves to find the speed of the car. This is the actually police using radar wave from, and reflected waves are shorter. Bats hunt moths in darkness by echo location and the Doppler effect. Some moths are protected by thick covering of a fuzzy scales that deaden the echoes. This is the real example of Doppler effect. In light, the Doppler effect also occurs for light. When a light source approaches, there is an increase in its measured frequency. When it recedes, there are a decrease in its frequency. When a source moves towards you, do you measure an increase or decrease in wave speed? You must know about these incidents. Neither, it is the frequency of a wave that undergoes a change, not the wave speed. So how does the apparent frequency of wave changes as a wave source moves? Now we'll discuss when observer is at rest and source in motion. When the source when the source moves towards the stationary observer, suppose a source S is producing sound of pitch n frequency and wavelength lambda, then the velocity of sound is b. Let the source move with a velocity a towards the observer in 1 second, and waves will be continued at a length b minus a. This is the actually, and waves will be contained in length b minus a. Actually, as distance equals to velocity multiply time, but in 1 second, distance equals to velocity. This is why b minus a length. And apparent wavelength will be velocity, apparent velocity divided by frequency, b, from b equals to f lambda. This apparent pitch will be apparent frequency equals to b divided by lambda dash. So apparent frequency equals to, putting the value of lambda dash from here. So we get n dash equal to b minus a into n. Thus the apparent pitch of the note increases when the source moves towards the stationary observer. This is the actually example. This is the velocity, this is the source, and this is the observer. When source moving towards the observer, then velocity become b minus a in 1 second. Now when the source moves away from the stationary observer, suppose a source S is producing a sound of pitch n, that means frequency n and wavelength lambda, the velocity of sound is b. So let the source move with a velocity away from the observer in 1 second, and waves will be contained in a length b plus a, because in 1 second distance equals to velocity multiply time. So distance equals to velocity multiply 1. This is why this is the distance. And the apparent wavelength will become lambda dash equals to b plus a divided by n, using b equal to f lambda. So lambda equals to what? Lambda equals to b by n. That, but apparent velocity b plus a. This is why. Now this is the when source moves away from the observer. Okay, this is the source moves away from the observer. This whole distance is b. Okay, in 1 second. But after moving away from observer, the distance is b plus a in 1 second. Okay, distance equals to velocity multiply time. This is why velocity multiply 1. This is why b plus a distance. So apparent pitch will be n dash equals to b by lambda dash. Just putting apparent pitch will be b divided by b plus a into n. So thus the apparent pitch of the note decreases when the source moves away from the stationary observer. More for the same values of b, a, n, the values of n dash in equation 1 will be different. Again, another condition, when the observer moves towards a stationary source, that means source at rest and observer in motion, the number opposite to the first one. So suppose a source as is producing a sound of pitch and wavelength lambda, the sound of velocity b, let the observer moves with a velocity b towards the stationary source. In this case, the observer receives more number of waves in 1 second. The apparent wavelength will be n plus b by lambda. Okay. So this is the source and this is the observer, and their length will be at time 1 second b. But after moving, if the observer moving away from the source, then distance will be shorter. So in this case, apparent pitch will be b by lambda plus small b by lambda. So n dash will be this, and but b equals to f lambda, that means n lambda. So lambda equals to b by n, putting the values we get this. Thus the apparent pitch of the note increases when the observer moves towards the stationary source. Now second part, when the observer moves away from a stationary source will be stationary. Suppose a source S is producing a sound of pitch and wavelength lambda, and the velocity of sound is b. Let the observer moves with the velocity b away. This is the source and this is the observer. So their distance will be b in 1 second. But if the observer moves away from the stationary source, then this will be the figure for that. Now from the stationary source, in this case, the observer receives less number of waves in 1 second. This is why the apparent wavelength remains the same. The apparent frequency will be n dash equals to n minus b by lambda. B is the actually length in 1 second for the moving away from the source. So n dash equals to b minus lambda divided by b minus lambda. So n dash equals to b minus b divided by lambda. But using lambda equals to b by n, we get this. So from equation 2, we get the apparent pitch of the note decreases when the observer moves away from a stationary source. Now, when both the source and the observer are in motion, when the source moves towards the observer and the observer moves away from the source. Suppose both are moving. Suppose a source S is producing sound of pitch and wavelength lambda. The velocity of sound is b. The velocity of the source is a and the velocity of the observer is b. In this case, let the source move towards the observer with a velocity a and the observer move away from the source with a velocity b. The apparent wavelength will be lambda dash equals to b minus a by n. So this is the source and this is the observer. Their distance in 1 second is b s equal to bt, s equal to b velocity multiply 1. This is why velocity equals to distance. Now if source moves towards the observer and observer moves away from the source by b length, and this is the length. So apparent pitch will be b minus b by lambda dash, and in this way n dash equals to b minus b, lambda dash equals to, putting the value of lambda dash, we get this one. So special case from equation 1, when the source and observer move towards each other. In one, taking b to be negative because opposite of previous condition, b minus b plus b divided by this. When the source and observer move away from each other, just taking a negative, we get the condition n dash equals to b minus b divided by plus. Source moving away from the observer and the observer moving towards the source. In the equation, taking both a and b is negative, we get the condition. Now effect of wind velocity. Suppose the wind is moving with a velocity w in the direction of propagation of sound. The apparent velocity of sound will be b plus w. In all relations, in place of b, if we put b plus w should be used if the wind is blowing in direction, and the velocity of sound will be b minus w when if the wind blowing in the direction opposite to the direction of propagation of sound, we have to use b minus w in the place of b. The general relation of apparent pitch will be this, b minus b divided by b plus. So Doppler effect in light we have discussed in our previous slide. This is the application, velocity and rotation of the sun, discovery of double stars, redshift. This is the application. Saturn's ring is due to the Doppler effect. I will discuss some real life example. A motor car sounding a horn at a frequency of 100 Hz moves away from a stationary observer towards a rigid flat wall with a velocity of 36 km per hour how many beats per second will be heard by the observer. The velocity of sound in air is 350 meter per second. The given condition is B equals to 350, A equals 36 kilometer per hour, that means 10 meter per second, and frequency will be 100 hertz. Here the observer receives sound of apparent frequency N1 from the moving source directly, and also sound of apparent frequency N2 from the sound waves reflected from the wall. So N1 equals to N into B plus B divided by B plus A. Just putting the values, we get N1 equals to 97.23 hertz, and N2 equals to, we get 102.9 hertz. Number of beats will be N2 minus N1 equals to 5.67. The apparent frequency of a whistle of an engine changes in the ratio 6:5 as the engine passes a stationary observer. If the velocity of sound is 352 meter per second, calculate the velocity of the engine. When the source moves towards the stationary observer, this. When the source moves away from the observer, then B plus A. This may be A. So dividing by 1 by 2, we get, this is actually wrong, printing mistake. This will be A. B plus A divided by B minus A. We get the result. Now another example. Two trains traveling in opposite direction at 100 km per hour each cross each other while one of them is whistling of the frequency of the note is 800 hertz. Find the apparent pitch as heard by an observer in the other train. So before the train cross each other and after the train have crossed each other, what will be the apparent pitch? So velocity of sound given 340 meter per second. Here 340 I equals to 100 kilometer per hour, that means 250 by 9 meter per second, and B equals to 250 by 9 meter per second, and equals to 800 hertz. In the first case, the source and the observer are moving towards each other. Therefore, N dash equals to N into N means frequency here, B plus B divided by B minus A. N dash equals to, just putting all the values here, we get this. In the second part, in the case, the source and observer are moving away from each other, just opposite of this equation. Okay, here plus minus, but we have to use minus plus, just opposite. Putting all the values, we get the result. Now another example, same example. Calculate the actual frequency of the note given by the whistle. Velocity of sound is this. We have to find out the N. N1 minus N2 equals to 500. N1 is the apparent pitch when the train is approaching the observer, and N2 is the apparent pitch when the train is moving away from the observer. So we get the equation, and this. Another example, a person is standing on a railway platform. An engine while approaching the platform blows a whistle of pitch 660 hertz. The speed of engine is 72 km per hour. Velocity of sound 350 meter per second. Calculate apparent pitch of the whistle as heard by the person. Velocity would be this, and A equals to 20 meter per second. So if the source is moving away from a stationary observer, we must know about this. Apparent pitch will be B divided by B minus N, just putting all the values. Similar example. When the source moving away from a stationary observer, B plus A. Calculate the actual frequency of the whistle. The source is moving towards a stationary observer. Similar example. Both are moving, the source and observer are moving towards each other. Two aeroplanes A and B are moving away from the another with a speed of 720 km per hour. The frequency of the whistle emitted by A is 1100 hertz. Calculate the apparent frequency of the whistle as heard by the passenger of the aeroplane B. velocity of sound is this 350. So, since the source and observer are moving away from one another, this is why using this formula. Similar example, and this is also similar one. This is left for you. Number of beats are heard by A n minus n2. Motor car find, calculate the difference in the frequencies of the notes heard by him. When the source is at rest and the observer is moving towards the source, show that the moving observer will receive a wave whose apparent frequency f naught is given by this, where f equals to actual frequency of the wave emitted by the source and b is the velocity of the wave through the medium of which is at rest. V naught is the velocity of the observer towards the source with respect to the medium. B, what will be happen when the observer is moving away from the source? The source observer is moving with the velocity v naught towards the stationary source S. Then the source S is emitting wave which are traveling through the medium velocity v. Suppose V is the observer and S is the source, and observer is moving towards the source with a velocity v naught. So in this case, we know V equals to f lambda, where lambda is the wavelength of the wave and the distance between the adjacent crest. If the observer were at rest, he would have received f number of crest in unit time. So since the observer is moving towards the source, he will receive more number of crest in unit time. The increase in the number of crest received by the observer in unit time is b naught by lambda. Therefore, apparent frequency will be original frequency plus this apparent frequency b naught by lambda. So we get the proof. Now, second part, when the observer is moving away from the source, the apparent frequency as received by the observer is f naught equals to f minus b naught by lambda. Now, when observer is at rest, the source is in motion towards the observer, show that the apparent frequency will be this. Similarly, when the source is at rest, the successive wave crest emitted by it are one wavelength lambda apart. When the source is moving towards the observer, the distance between adjacent crest is decreased. By the time the source travels in one cycle, time taken in one cycle is 1 by f. The distance traveled was by the source in the cycle is bs by f. Thus, the apparent wavelength for the source will be lambda s is given by lambda s equals to lambda minus bs by f. So, frequency of the source will be b by lambda s equals to this. Similarly, we get the second part. show that the Doppler effect is greater when the source approaches a stationary observer than when the observer approaches the stationary source with the same velocity. When the source approaches the stationary observer with the velocity bs, the apparent frequency is this. When the observer approaches the stationary source with the velocity bs, then the apparent frequency will be this. Now, difference between these apparent four frequencies is this. So, from this equation, you must have source frequency greater than observed frequency. This is another application. This is another one. This is left for you. This is the another example of Doppler effect. This is the supplementary problem for you. So from this lecture, we have studied actually what is Doppler effect. The Doppler effect occurs when a source of sound is moving with respect to the observer. A source moving towards an observer appears to have a higher frequency and the shorter wavelength. A source moving away from an observer appears to have a lower frequency and longer wavelength. Remember it. So this is the at rest and fire truck moving towards the source. In that case, if the source here and distance equals to d equals to lambda, source fixed, if we can figure out what the change in the wavelength is, we also may know the change in the frequency. When the source is approaching, the observed wavelength is shorter. So lambda dash equals to lambda minus velocity of source. So then the observed frequency will be f dash b by lambda dash. B equals to f lambda, we know. Now the change in the frequency is given by f dash equals to f by 1 minus source velocity, source approaching higher than frequency. And similarly, the source is moving away from the observer. We get this. So if the observer is moving with respect to the source, things are a bit different. The wavelength remains the same, but the wave speed is different for the observer. So this one, change velocity goes to velocity plus velocity of observer when the observer is approaching. So in that case, pitch or frequency, apparent frequency will be this. For an observer moving towards a stationary source, this one. And if the observer is moving away, just minus. Here plus and there minus. This is the example of you. Example. All four equations are in the Doppler effect can be combined into one. You just keep to mind that back of the sign. Approaching means higher frequency, apparent frequency greater than f, and receding lower frequency. Apparent frequency will be less than the original frequency. So thanks to everybody, and okay, bye for today.